and the brute force method. Brute force. I already mentioned this method several times. Yeah, but the first time when I mentioned it, I said on module 3, I was wrong. Actually, it's here, module 2. All right, not module 3. But the biggest topic in this module is study algorithm efficiency. It is very abstract. Asymptotic notations. Our part B. Not today. Today, I do not introduce that asymptotic notations. But next time, part B, I need to introduce asymptotic notations. So today in part A, our topic is problem solving from experience and elimination. I need to put this and elimination method. 8.1, selection sort. This is the first time we work on the sort problem. From module 1, we did one search problem, right? Sequential search. And we did one selection problem, finding the minimum problem. Now, our first sort problem, selection sort. Actually, for most of you, you learned another sort algorithm in your CS3250. Because I taught that once before, 2250. All right. That is the bubble sort. Remember, in 2250, bubble sort. You learn that, right? But in this class, I will revisit this bubble sort another time. In our module 3, I will revisit this bubble sort. If it's module, could be wrong, but approximately 2 or 3, module 2 or 3. I couldn't, memorize clearly, All right, Although that is an old algorithm, but there is some new concept to be introduced. Sometimes I talk about some old questions. There is some good reasons, because I need to introduce some new concepts, new views, and new ideas. All right, so let's start our 8.1 selection sort first. Our problem number 4, sort an algorithm. Let me give you the question first. Pretty simple. Given an array, still our usual representation, capital A, bracket with indices from 0 through n-1, n elements. What do we need to do? How to sort it in ascending order. Ascending order here by default, if I do not mention what order, by default, we mean ascending order. If we like to do something in descending order, I have to say that word, descending word. If I do not say any word, ascending or descending, by default, we mean ascending. Okay, in my questions, sometimes I just say in order. All right, in order means in ascending order. All right. Next, the problem type is sort. The reference, I give it to you for you reading, if you like to do some reading in a textbook, section 3.1. All right. work and analysis. At the beginning, I like to talk about some general problem-solving guidelines. So here, I give you 2 guidelines. The first one, find a solution from our experience. That's common, right? For our human to develop knowledge, usually what we do, we develop some new knowledge and based on our experience from old knowledge. That's quite common, yeah. But think about if you do not have a lot of experience, yeah. If someone even very smart, but that person does not have a lot of experience, then that person cannot go very far. Without experience, that means you need to develop everything from scratch. Think about that. You don't have the, background. You do not have the foundation. You have to develop everything from scratch. You can think about how hard it is. With a lot of experience, then our starting point could be pretty high. We can move the bar, move our starting point in a relatively high level. All right, so here we have that situation. Yeah. To sort an array, we need to apply some knowledge we have already learned in this class at this point. That is module 1. Yeah. So we need to connect to our module 1 experience and the knowledge there. Yeah. All right. Then if you can connect, yeah, how to study it, right? How to find the critical step, explore properties. You need to discover some key property, key properties. Yeah. So in this class, you will see when I explain my problem-solving details, you will notice I will spend a lot of time trying to discover some critical properties. Yeah. So these 2 steps, very general, almost true for all our problem solving. All problem solving, at least in this class. Yeah. So I say the guidelines. Yeah. Here I do not say strategies. I do not say we take this strategy because too broad, too general, right? For almost all problem-solving questions, we can, take these 2 guidelines. Yeah. But for strategies, I like to make them more specific, right? With respect to a particular problem, I like to make it more specific. Yeah. For different questions, we may apply different strategies, usually, right? It's not like, one strategy you can solve all problems. Yeah, that's not realistic. Yeah. All right, let's do the work. This method, commonly used method, backward thinking. Yeah. Many of you are used to it, right? Backward thinking. Yeah. Yeah. Here, we can do the backward thinking. So in which way? You can imagine, assume the array has already been sorted. Then what property can we discover? Yeah. Sometimes we need to do it in this way. Not always, right? Not always. This is one commonly used method. Yeah. Yeah. But it does not mean you always try this method. One of your options. Yeah. Here we can treat as we try to build up our toolbox. In our toolbox, we need to have a many tools. Yeah, this is one of the tools in our toolbox, backward thinking. Yeah. So we assume the array is sorted. Yeah. Yeah. And another assumption we also like to add to this problem, we assume distinct elements in this array. All elements in the array are distinct. That sounds like a little more assumption, right? Because the original question, original problem, we do not have this assumption. We are allowed to have duplicate elements, right? Yeah. Original question. So you modify your question in this way. Is it okay or not? Yeah. Let me explain why we can do things like this. Yeah. Here, my explanation is in this way. Actually, this way is pretty common in general problem solving. Yeah. First, why people like to do that? Not just we, people like to do it in this way for convenience. That's the top reason. First, for convenience. Why? Because if we assume distinct elements in our discussion, we do not need to worry about the duplicate elements. So that saves a lot of discussion. All right, so that's the first reason. Yeah. But second thing we also need to consider, that is, how about when we are given an array with duplicate elements, right? Yeah, that's possible. Yeah. Don't worry, if we are given an array with duplicate elements, we can modify our solution with distinct elements, tweaking a little bit to cover duplicate elements. How about that? How about that? Right? That is our approach. Okay. Yeah. Here, let me write the approach. All right. Yeah. Just a minute. Let me still lay down my laptop in a comfortable position so I can write my handwriting. All right. Now here, let me explain our approach, general approach. All right. The approach is like this. First, we may not solve the original problem directly. We solve an approximate problem. Let me call approximation. First, we do approximation first. For some reason. Yeah. There are many reasons we do not solve the original problem exactly. We solve a problem that is close to our original problem. All right, yeah. Because the main reason is if we do that approximation problem, we can make it easier, relatively easier. Yeah, right. But at the end, we have to go back to the original problem, right? Yeah. We have to go back to the original problem. So after that, then we do another step to back to original problem. Yeah, I called bridge the gap. Bridge the gap. There is a gap, right? There is a gap between approximation and our original problem. But that gap, if our approximation is very close, then that gap is very small. So if we do that bridge the gap step, it is pretty easy. Yes, so this is a commonly used approach. So here I spent quite some minutes, talk about that. Later, this approach we will use many times. Yeah, many times. Yeah. All right. Yeah. Next. How to connect this problem to the minimum problem. Yeah. In our module 1, yeah, think about in our module 1, we learned the minimum problem, finding the minimum, and we learned, polynomial problem, right? But polynomial problem has nothing to do with our current problem. Yeah. So we bypass it. And the linear search problem. Yeah. It looks like we can borrow some experience from the minimum problem. Yeah. All right. So we want to do the connection here. Yeah. All right. Here, before we do the connection, we need to make some observation to discover key property. Yeah. Based on the assumption, yes, backward thinking assumption, we assume the array has been sorted. And we also assume distinct elements, so we do not consider equal case. Yeah. So we have this sequence of inequalities, right? Yeah. Try your best to observe the key property connecting to our minimum problem. Is there any relationship? This inequality chain to our minimum problem? Look at that. Yeah. Yeah. So you will see A0 is the minimum, right? A0 is the minimum. Okay. Yeah. And we know how to find the minimum, right? Yeah. We know how to find the minimum. We just apply our solution, finding the minimum solution. We get A0 immediately, right? We get A0 immediately. Okay. Yeah. Or we get the minimum element in the given array immediately, right? Does it help? If we can find the minimum of the given array, does it help? Think about that. It helps, right? Yeah. Yes. That's the connection. That's the connection. You can see at least we move one step forward. With the minimum problem solution, we move one step forward towards our final solution. Yeah. All right. Yeah. Oh, enable. Yeah. Transcript. All right. Yeah. Enable. All right. Next, I'd like to introduce a concept called in-place concept. Yeah. In-place. Yeah. From this phrase, you can guess the meaning. Yeah. It matches our natural language understanding. In-place meaning. Yeah. But here I like to repeat its meaning another time. Yeah. The element is placed at the position when the array is sorted. Then we call this element is in place. Yeah. What do we mean an element is in place? Yeah. All right, so let me use a few more sentences to explain this concept. Yeah. Given an array, yeah, we know before we do any sorting work, the order of the elements is pretty much random, right? Random order, yeah. So then we do a lot of work, basically do comparisons. Yeah. At the end, we make the whole array sorted. in order. All right. When all the elements are in order, they have their corresponding positions in the ordered array, right? Yeah. Each one has its own right position in the sorted array, right? All right. Now we use this concept, in-place concept, to describe during our work. Yeah. Because when we do our sorting work in the middle, we may not get all the elements ordered, but we may get some of the elements in their right position when the array is finally sorted. Then we want to refer to those elements that are already in the right positions. So we give a name for it, in-place name for it, for our discussion. All right. Later, after we learn this concept, later, when I talk about some element is in place, then I do not need to use a lot of sentences to explain what's the meaning. Yeah. So we know its meaning, right? Yeah. So now, at this point, we can use this term, in-place term, we can say, after we apply the minimum problem solution, we can make A0 in place. How about that? A0 is the minimum, so we can put A0, that element, in place. How about that? All right, yeah. In other words, after we apply the minimum problem solution once, we can make one element in place. How about that? Yeah, so that's the progress we can make through our minimum problem solution. Yeah. All right. Yeah. Next. Yeah. Then another useful method I want to talk about called elimination method. Yeah. Elimination method. Yeah. Pretty straightforward, right? So we do some elimination. Yeah. All right. And later you will see I will use this elimination method many, many times, and it is pretty effective. Yeah, it looks like, not fancy, right? Yeah, do elimination. So everybody has experience doing elimination in their real life. Yeah, yeah. But here in this class, you will see, if I do not emphasize, here I really like to emphasize this method. If I do not emphasize, most of you may not be aware of it, this method. Even when you are in a situation that you need to use elimination method, but you may not be aware of it. Okay, yeah, yeah. So you will see, yeah, later you will see, yeah. And for some relatively hard questions, and this one, the impact of this one, could be quite magic. Yeah. So you will see some magic things. Yeah. All right. Here, how do we apply this elimination method? Think about that. After we determine that A0 is already in place, so we put it in its right position. When we work on the remaining elements, do we still need to worry about A0? When we work on the remaining elements, we don't need, right? If we do not need to look at A0 again, why we need to still put it into consideration? We do not need. We can remove it out of our consideration. That's the elimination method. Okay. After we put it in place, we eliminate it in our array to be processed, right? Yeah. We complete processing A0. So we should remove it from the remaining array or remaining subarray to be processed. That's the idea. All right, yeah, so let's continue. Then, when we look at the remaining subarray, after we eliminate A0, then we notice that A0 would be the minimum of the remaining subarray. Then you can see we apply the minimum problem solution another time for A1. How about that? The second time, we can apply the minimum problem solution again and again until we put all the elements in place. How about that idea? Think about that. How about that idea? We almost get there, right? Think about with this kind of analysis, we almost get there. All right? Yes. Let's complete the work. All right. So our conclusion so far, in each round, we place one element in place. That's what we can do each round. What is each round? Yeah. Each processing round that we apply the minimum problem solution to find the minimum. Yeah. If I want to recover all the hidden words, I like to say in that way. Yeah, that's the each round meaning. Yeah. All right. Next, we want to really solve the whole problem. Yeah. The question, how to make all elements in place? That's sorting, right? How to make all elements in place. Yeah. In other words, this question just another way to describe the sorting step. Yeah. All right. Yeah. Let's do the work. Yeah. All right. Yeah. Here I draw a diagram. Yeah. The first time we find the first minimum, so we put it in place. All right. Then for the remaining subarray, we apply another minimum problem solution. So we put a second minimum in place and so on. Okay, one by one, every time one more element is in place until we put all elements in place. That's the sorting. That's the whole procedure of sorting based on the minimum problem solution. How about that? From our experience. So we derived a new solution. Yeah, we say new solution because before we discover it, we do not know it, right? We do not know about this new solution. Yeah, but we apply our old experience, minimum problem solution, old experience, and we put things together, and finally we get this new solution. Think about this procedure. Yeah. The conclusion. Yeah. Where all the elements in the array are in place, the array is sorted. Yeah. Pretty obvious. Yeah. The array is sorted. Yeah. Because when we define in-place concept, we use that sorting fact, right? The sorting fact. When the whole array is sorted, then we look at their positions when we define this in-place term. Yeah. All right. So we complete the solution. Yeah. All right. Next, efficiency analysis. We want to see how many comparisons do we need. Yeah. Actually, pretty easy. Pretty easy. Yeah. We just apply still in the result when we find the minimum, how many comparisons do we need? Find the minimum of an array with n elements. We know n minus 1, right? Yeah, the result, we can use that directly. Yeah, find the first minimum, n minus 1. Yeah, the number of elements in the array, minus 1. The second minimum, because the remaining elements in the array, in the current array, only n minus 1. So n minus 1 minus another one, n minus 2, and so on, n minus 3, and so on. Okay, yeah. The second to last 1, the last one 0. Yeah, like that. Okay, let us add up all the number of comparisons. So we get total 1 plus 2 plus through n minus 1. So we have this 1/2 times n times n minus 1. That's the final efficiency number for this sorting algorithm. This one we call a selection sort. Why selection sort? Because the minimum problem we call a selection problem, right? Yeah, the minimum problem is a special selection problem. So we apply that special selection problem to do the sorting, and that is our main step. So we call it selection sort. Yeah. All right. The best case, think about this. The best case, the worst case, and the average case for this solution. Yeah. You will see they are all the same. Yeah, because there is only one possibility. Finding the minimum each round, there is only one possibility. So we can say best case, worst case, average case, all the same expression, this 1/2 n times n minus 1. Yeah, same expression. All right, yeah. Then at the end, I like to talk about this elimination method a little bit. Yeah. Do some summary here. Yeah. First, the goal. What is the goal of the elimination method? After elimination, we can reduce the problem size. Problem size. Here, the problem size, we mean the number of elements in the array. Yeah. The problem size in this question, this problem, that means the number of elements in the array. So here the size is n elements in the array. Yeah. Later, we will see the problem size has another different meaning. Yeah. So the number of elements in the array, that is the main, most frequently used case. Yeah. But there is another less frequently case. I will talk about that later. Yeah. Yeah. All right. And why reduce the problem size would help us, right? Yeah. Why reducing the problem size would help us solving the problem? Yeah. Yeah. It's pretty easy because the smaller the problem size, the easier the problem. The larger the, in general, right? Usually in general, yeah. But you know, this direction is pretty much correct. Yeah, the direction is pretty much correct. Yeah, we cannot say 100% correct. Yeah, because there is some exception. Yeah, probably for some special problem, we may have some exception. Yeah, but this direction, yeah, pretty much correct. Yeah, the smaller the problem size, the easier the problem. Yeah. And another thing we notice that when some elements do not change the outcome. Yeah, think about after we put an A0 in place, then we do not need to consider A0 again. Yeah, because after we move one step forward by placing A0 in place, then for the remaining work, A0 would not change the outcome of our remaining work, right? So we should remove it from our consideration. Yeah. So those elements can be eliminated from the consideration. Yeah. So that is what we learned from this elimination method. Yeah. All right. So we complete our first topic. Yeah. All right. So any question? Yeah. Let us move to the next topic. Is elimination the approximation answer different? All right. Elimination and approximation, if you try to compare them, quite different. Quite different. Approximation, yeah. Think about approximation. We describe a problem that is slightly different from the original problem. That's approximation, right? Yeah. But elimination, you can, try to pay attention to the subtle things. The elimination, we try to reduce the problem size. Yeah. Some elements irrelevant, right? Yeah. Because after we do some work, some of the elements are already irrelevant for the remaining work. So why we need to, waste our energy on those elements without any relation or any benefit for our remaining work, right? Yeah, so that's elimination. So I feel, yeah, good. Yeah, I feel, yeah. So yeah, here for this class, we need to really pay attention to the details. Yeah, so here, actually, my answer quite different. Yeah, approximation gives us, yeah, let me use another angle to understand it. Approximation, that pretty much it gives us a direction, an approach. That's why I say approach, the direction to work. Now, when we solve a problem, we try to, approach that problem step by step. Okay, yeah. Because if we strike on the original problem directly, it could be very hard. All right, very hard. We want to reduce the difficulty of the problem. All right, yeah, we want to reduce the difficulty of the problem. So we modify it to make the problem slightly easier. Yeah, oh yeah, there, Carly, yeah, from another point of view, these two things have some similarity from another point of view. Regarding reducing the problem difficulty, they are the same. How about that? Elimination helps us reduce the problem difficulty, right? Approximation also helps us to reduce the problem difficulty. Yeah. In that respect, then we say they have the similarity, all right? But in general, we do not say they are very close. They are two different concepts. All right, good, yeah. Because when you ask questions, that would help us understand things better, yeah. All right, so let's move to the next topic. Impact of organized data. Impact of organized data, yeah. I mentioned this topic a little bit in our module 1 when I talk about data structure. Data structure, at that time I said data structure helps a lot, okay? The data structure helps us organize the data. With organized data, we can do better. Yeah. But here we continue that topic. We will see with organized data, we can improve the efficiency of our algorithm. Yeah. All right, so let's look at the question first. Problem number 5, element uniqueness problem. Yeah. From the title, you can guess the content of this problem. Element uniqueness problem. Uniqueness. Yeah, it is related to duplicates, right? I mentioned the duplicate elements in our discussion of the previous problem, problem number 4. Here, we look at that uniqueness or duplicate elements, the opposite of uniqueness, duplicate elements here in this problem number 5. Yeah. Let me give you the problem description first. Given an array, as usual in this expression, the question, how to check if all the elements are distinct? It's a simple question. Okay, simple question. Yeah. But our goal, we do not just find a solution, we want to find a better solution. Yeah, that's our goal. Yeah. I believe everybody can find the correct solution. Yeah. But we need to find a better one. Yeah. All right. Yeah. Here I give you the reference in our textbook, section 2.3. Yeah. All right. Method 1. Yeah. Here I like to use 2 methods, method 1 and method 2. So for the method 1, brute force method. Yeah. Everybody can do brute force. We do not need any special technique. Yeah. We just, based on our intuition, we just apply the basic operations in a straightforward way. Yeah. All right. Definitely in brute force method, we do not organize our data. We just work on our data directly. Yeah. All right. That means in the preparation step, yeah, usually we treat this step, yeah, when we do organize the data, this step, we can treat as the preparation step. Right? Yeah. Data preparation. All right. But here we do nothing at data preparation. Yeah. That means we do not pay anything in data preparation step. All right. Yeah. All right. Yeah. But next, let's just do our work immediately. Yeah. All right. In a straightforward way. First, yeah, we can imagine we have some example array. So here, the numbers I put here, that's just a example array. Yeah, I put concrete numbers. Yeah. When we check, oh, here, I like to point one thing out before I go to the details. I point one thing out. So that is, yeah, that is the machine does not have eyes. All right. Why I say that? Yeah. You know, based on my experience, yeah. When I taught this class many times before, I noticed that I need to explain this sentence many, many times to my students. Yeah. What does it mean? Yeah. Yeah. With this example, when we see the array given here, you know there are no duplicate elements immediately, right? because you have eyes, you can see. After you see these numbers, you can get the answer immediately. There is no duplicate element in this array. All right, but machine does not have eyes. All right, when you write your program, you run your program in a machine, right? The machine just execute instructions in your program. Even you pass the numbers in this array to the machine cannot see the things like you. All right, the machine just execute instruction by instruction from beginning to end and get a final result. All right, that means the machine cannot see before the machine implement the instructions. The machine cannot see these elements are distinct. That's the meaning I like to convey here. Later, there are many other places I need to use this sentence to explain. The machine does not have eyes. All right. That basically means something you can see easily, but machine cannot. Something for you it is obvious, but for machine it is not obvious. All right. Yeah. Okay. When we consider the first element, the first round processing, we want to see if 0 is repeated anytime in the array. To do that, we need to do n-1 comparisons, right? Compare 0 with 1, 2, 3, and all the remaining elements. So we need to do n-1 comparisons, right? After we complete processing 0, we need to process the second element, 1, and we need to do n-2 comparisons, and so on. All right, yeah. So in this pattern, at the end, 1 and 0. Yeah. If we add up all the comparison numbers, overlap. I have to erase it. All right. This sentence, it is important, but I have to erase it. All right. Analysis of efficiency. Best case efficiency first. The best case when the first two elements happen to be equal. After the first comparison, we get the answer. We get the answer, yes. The elements in this array are not distinct by one comparison. Worst case efficiency, when the last two elements are equal, we have to do all the necessary comparisons until we compare the last two elements. And we need this many comparisons. All right, best case, worst case. How about average case? Average case, you can think about it. You can think about it. But when you think about it, you may need to make some assumption. The answer relies on some reasonable assumption. If you want to try by yourself, I like to refer to the linear search solution. You may go back to look at our linear search solution. How do we find the average case efficiency for the linear search or sequential search? After you understand that solution well, then you can find some similarity between this question and that linear search one. All right. So here, I do not try to do it here to save some time. Yeah, but later when I have a chance, I may talk about it. Yeah, in our problem session, for example, yeah, problem session, I may give you, many examples to help you solve different questions, especially relatively hard questions. Yeah. All right. Yeah. Next, number 2. Method number 2. Yeah. Pay some cost to organize data. Yeah. So in our data or organization step, data preparation step. Yeah. Data preparation step. We are willing to pay some cost to get our data organized. Yeah, so that's the second method. Yeah, all right. Method number 2, investment in data structure. Yeah, so we pay some cost, all right, but later we will get something back. We get something valuable back. That is, we can reduce the number of comparisons. Yeah, so we treat this step, the cost we pay here, as the investment. Yeah. All right. What kind of investment? We sort the array first with certain cost. Yeah. How much cost do we pay when we sort this array? If we apply the selection sort, we just completed, yeah, selection sort, that will be 1/2 times n minus 1. Yeah. That cost, you can see the same as the worst case cost, right? In method 1, already worst case. Definitely, this kind of performance is not acceptable. Too bad. In our preparation, we already paid that worst case cost. All right? Yeah. So we should not consider selection sort. Yeah. But when we sort this given array, we like to use a better sorting algorithm. Better sorting algorithm. We haven't learned at this point, but we can imagine there is some better sorting algorithm available, so we can apply it. Yeah. Here, I just give you the result directly, and we will learn this result later. Yeah. Here, later we will know to sort a given array, the reasonable cost we can pay is n log n. N log n. Now, this cost can cover the worst case. Even the worst case, this cost is enough. All right, yeah. Yeah. We will learn, yeah. Here we just use the result directly. All right, yeah. Yeah. Okay, yeah. And we know this cost is much slower than, not slower, much smaller than 1/2 times n minus 1 when n is large. When n is large. When n is small, n log n may not be greater than 1/2 times n minus 1, but when n is larger and larger, you will see the first expression comparing with the second expression will be smaller and smaller. Yeah. And actually, if we take the ratio of these two expressions and look at the limit where n approaches infinity, we will do that quickly in the same module. In this module, we will compute many limits. Yeah, this will be one of them. Yeah, you will see the limit will be 0. The ratio, yeah, limit approaches to 0 when n approaches to infinity. Think about that. How smaller, yeah, in their comparison. All right, yeah, that means we make big improvement. If we make this kind of investment, we will do some really smart investment. All right, the next step, because after we pay this much as investment, we can assume we have an ordered array. We have organized the data. What do you mean organized the data? Ordered array, that means in this question, the data is organized in ascending order, right? Yeah. So the question becomes, yeah, how to check if there is any element repeated in an ordered array. How about that? In an ordered array this time, because we pay a lot of cost, we pay. It's not cheap. N log n, we cannot say n log n is cheap, right? Yeah, we pay a lot of cost. Yeah, we expect to get something pretty big as reward, pretty big. All right, yeah, okay, yeah. So let's take a look. Now we can apply our checking step, right? Duplicate checking step here. All right. Here we assume we have an increasing ordered array. Observation, do a simple observation. We pretty much see the, endpoint there. Yeah. So just make this simple observation. Yeah. When we do the checking, we only need to compare 2 adjacent elements. How about that? 2 adjacent elements. Yeah, you do not need to compare 2 elements that are not adjacent. Think about that. Think about if there are duplicate elements. After you do the sorting, then you will find there must be 2 adjacent elements with the same value. How about that? How about that observation? With a little imagination, in your mind, you need to think about that picture in your mind. Yeah. Okay. Yeah. So here you can see this step is pretty important. Yeah, pretty important. I like to point out this step or summarize this step as change from global comparison to local comparisons. How about that? Global comparisons, in our method 1, we do global comparisons, right? Yeah. So A0, compare A0 with A, n-1, think about that. That kind of global comparisons, right? Far distance. The distance between 2 elements could be, anywhere in the array, right? But here, we don't worry about far distance comparison. We only need to look at the local comparisons. What do you mean local comparisons? The comparison between two adjacent elements. That's the local comparison. How about that? When we do this change from global comparison to local comparisons, we can reduce the number of comparisons significantly. Now think about that. Yeah. Now, after this observation, we can write a simple pseudocode. One for loop. Yeah. One for loop, we can find the answer. Think about that. One as simple as this. Yeah. So I think you understand this pseudocode, right? Yeah. Return true or false. Yeah. If it is true, that means there are some duplicate elements. If it is false, that means there is no duplicate element in this array. That's simple, right? Yeah. Because here with this comparison, that is the local comparison. Think about that. Local comparison. Okay. Yeah. All right. Then we can easily see the number of elements we need at the most for n-1, right? Because this function, when we implement this loop, we can return earlier, right? The worst is n-1. Yeah. The worst is the n-1 comparison. All right. Yes. So you can see, yeah, all right. Yeah. Yeah. The next topic. Yeah, because it is pretty close to the end of the class. So I mean, yeah. All right. So the answer, the final answer, all right. Yeah. We need to add up two parts. Preparation step, we pay this much cost. Yeah. Actually, this log is log base 2. I didn't write the base of the log, but yeah, I mean log base 2 of n. Yeah. Then plus the worst case of the second. Yeah. Yeah. Yeah, we can say this expression, yeah, for the worst case. Yeah. In general, we can only do better. Yeah. This is for the worst case. Yeah. All right. Then, yeah, later we need to compare this one with this one, our method 1 expression, this one. Yeah, compare these two, but here I need to bring back a concept we learned in our module 1, that is the dominant term concept. Dominant term concept. Yeah. Why I mentioned the dominant term? Because in this class, algorithm class, many times when we do comparisons, we do not do exact comparisons. We do approximate comparisons. Here, another place to use approximation. We do approximate comparisons. We do not do exact comparisons. Yeah. Why is that? Yeah. So you will see. Yeah. 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 Let me explain. Yeah. So here we have just 4 minutes, right? 4 minutes. Yeah. Let me see how much I can go in the remaining 4 minutes. Yeah. All right. So dominant term. The first term in this expression is the dominant term. Yeah. The second part we treat as the minor part, and we can ignore it. In our comparison, we can ignore it. All right. All right. So we just compare these two expressions. Yeah. You may ask me why we can ignore the minor term. After we have the dominant term, when we do comparisons, why we can ignore the minor term. Yeah, I have just 3 minutes. Let me use about 2 minutes to explain why we can ignore the minor term. All right, yeah. Still, we connect to our real world experience. All right. In our real world situation, you do a lot of approximation, right? Think about your real life experience. Do you need to do a lot of approximation? Yeah. Many times you do not require things to be exact, right? You know, if it is pretty close, you may feel fine, right? Think about that in your real life experience. Here we have the similar situation. When we do comparisons, let's look at the minor part. How much percentage it accounts for the whole big part? Yeah, the minor part. Think about if the minor part takes about 0.1% of the whole part, yeah, of the whole, yeah, let's say the whole. The minor part takes just 0.1% of the whole. Are you willing to ignore it for the comparison? Right? Yeah, that's why, because the dominant term usually dominates in a way much more than 99.9%. Much more than dominant in a way, much more than 99.9%. All right. So your minor term less than 0.1%. Are you willing to ignore it? Yeah. If in your real life experience, you know, you do not require the minor part to be ignored as small as 0.1%, right? Yeah. Your threshold could be much larger, right? Your, you know, tolerance could be much higher than that, right? Yeah. Yeah. Later, I will explain why actually the minor term much less than this 0.1%. Yeah. All right. Yeah. Now we are at the end of this class. Just last sentence to let you know, I will post quiz number 1 soon, sometime today. Yeah. You can expect sometime today, you will see our quiz number 1 covering module 1 content. Yeah. All right. So that's it. Yeah. Let's stop here.